Hey everyone, it's Unit 8 Kinetics and Thermochemistry, and we're going to be talking now about thermochemistry. If you recall in class last time, we went through this particular chart and filled it out. This is an older version. It isn't the exact one we maybe did in your class, but it should still pretty much be exactly the same. We have 4 different variables. This lesson is going to be an opportunity for you to learn a little bit more about these variables and also to make sure that you understand how to use them mathematically. So we have 4 things. We have enthalpy, mass, temperature, and specific heat capacity. We've already gone over those, but they'll kind of come up again as we go through this lesson. The other reminder I want to give you is that enthalpy of a reaction is affected by any change in mass, change in temperature, or if you change to a different substance, perhaps it reacts or something else causes it to actually do that. So by definition, thermochemistry is just a study of energy actually transferring through chemical reactions. So we started off really talking about thermodynamics in general, so we said that there are in fact endothermic, exothermic reactions, as well as endothermic and exothermic processes, like melting and things. Those aren't chemical reactions, but they are changes in processes that are occurring. And so by studying thermochemistry, usually we're studying heat. And again, we're all talking about perspective here. When we say that something is hot, we're just saying that it is transferring energy into our body, and therefore it is making us feel the sensation of heat. But we don't say that, we just say I'm hot. Okay, rather than saying the air is such a high energy, it's transferring energy into me and it's too much. We just say I'm hot. Okay, so that's kind of a different perspective, but remember that we're talking about perspective, and usually when we're talking about thermochemistry, we're talking about the chemicals themselves. Temperature is measured by using heat transfer. We see it actually change, and that's how we figure out that temperature is occurring. Otherwise, something is not able to really be measured for temperature very easily. We use 2 scales, of course, Celsius and Kelvin, and to convert between them, we add 273 to Celsius, and we'll continue to use that as we go through this particular activity. So this is the formula that we're going to be using to calculate. We have delta H, we have let me highlight these. Delta H, we have mass, we have change in temperature, and we have specific heat capacity. Specific heat capacity we defined last time as being the amount of energy that it takes to increase the temperature of a substance. Specifically, and by real formal definition, it's the amount of energy required to raise the temperature of 1 gram of any substance or of that substance by 1 degree Celsius. So basically it's just a set unit for how much energy it takes to cause a change in temperature for that substance. Some things like water have a really high specific heat capacity, so it's super difficult to change the temperature of water, whereas things like metals have very, very low specific heat capacities. So when we're doing this calculation, we have the delta H, that's usually what we're calculating for, although some questions, of course, may have the overall energy or enthalpy and you're solving for something else. Mass of the sample matters, of course, because any change in the mass would change how big it is, and that's going to change how much energy it absorbs. Temperature changes, we always do final minus the initial temperature. Whether it heated up or whether it cooled down, it's still going to be final minus initial. And I will say this now, and I hope that you hear it. It can be negative. Okay, and that ultimately means that so can delta H, because if we put a negative value into the problem and then we multiply, it's possible for our final answer to come out being negative. We already saw from our graphs that if we have what we refer to, of course, as endothermic, then we're going to have a positive delta H. If we have an exothermic reaction, it is going to be a negative delta H. So I already mentioned it, but this slide allows you to write down the actual definition of it. This is the value that kind of determines how well a substance can heat up or cool down. Okay, and it's the amount of energy. Okay, so I'm going to be color coding some things here. The amount of energy. Oh, that's just writing. Okay, let's highlight. All right, go back. There we go. The amount of energy in joules required to raise 1 gram of a substance 1 degree Celsius or 1 Kelvin. So as a result, that's how the unit comes out. The unit comes out having temperature in it, having mass in it, and having the joules on top because it's joules per gram per degree Celsius. Okay, so this chart right here gives you some examples, common examples. Liquid water has one of the highest specific heat capacities of a lot of substances at 4.18. And then just to give you a frame of reference, down here we have a couple metals like iron, copper, and you know they heat up really fast and they have very low specific heat capacities. Threw together a couple practice problems here. We have our delta H formula, of course. I'm going to color code it again. We have our delta H, we have our mass, we have our change in temperature, and we have our specific heat capacity. Okay, so looking at the problem, it says a 3.0 gram, well, that's a mass. Okay, block of iron is heated from 283 Kelvin to 300 Kelvin. First things first, I want to identify, of course, that this is our initial, this is our final, okay? And they are temperature, so let's color those green. Oh my goodness, oh my goodness. Sometimes it's a simple thing. Let's color those green. It has a specific heat of 449, so that's Cp. And we can assume that that would be joules per gram Kelvin, because that's what's in the problem. What is the energy transferred in delta H? So in this problem, we're solving for delta H. So looking here, I'm only going to highlight this one. I plug that in. I would plug my mass in, of course, right here. Multiply that by final minus initial. Okay, don't forget, final minus initial. Okay? And then we plug in our specific heat capacity. Multiply. Get an answer, round it to 2 decimal places, 22.99 joules is our final answer. I threw another practice problem in here because in this problem it's a little bit different. You'll see more practice in class where we're actually solving for mass or solving for specific heat capacity or solving for initial temperature or something. But in this one, it's another one we're solving for delta H. I'm not going to highlight this one, but again, we plug in our mass as 55 grams. We have our final temperature minus initial temperature, and then our specific heat capacity. Multiply those, round to 2 decimal places, and we are good to go. Have a good weekend.